I am Shodish Das. I am faculty at Chennai Mathematical Institute with my colleague, Professor Ram Seshan at Chennai Mathematical Institute. I teaches mostly probability statistics related courses, and Professor Ram Seshan teaches mostly NLP, big data distributed computing, this kind of courses. And for last many months, we were talking about NLP issues, language models, and all. And one thing that came to my mind that with the LLMs, with the ChatGPT, as we are facing extreme changes in the industry, one thing it's getting clear to me, and I think many of you probably have realized that one area is also coming as an opportunity for the industry. When I'm saying industry, definitely for IT and IT-enabled services industry, and that is language models. Because, one example, and particularly small language models. One example I always give to my, colleague that about 30, 35 years back, one thing came in the banking industry called credit scoring. It was done by Crystal's and Moody's. What happened that time, pretty much all investment banks, uh, commercial banks, they bought the Crystal score or the Moody's score, credit score from them, and these companies, the credit scoring companies, became really big. But eventually, these investment banks and private in the, commercial banks and some of the very big nationalized commercial banks like State Bank of India, they started building their own credit scoring models. Today, their model has so much matured, they don't care to buy even credit score from Crystal or Moody's. They may buy, it's just the additional data point. Even if they don't buy, they work perfectly fine because they have, over the 30 years, their model has become so much matured, right? So similar thing I think is going to happen, that LLMs has developed by the big technology firms of US, and probably we will all these enterprises, big enterprises, are going to use these LLMs for solving our problems going forward. But eventually, the manufacturing industries, the pharmaceutical industries, the banking and financial services, everybody wants the previous panelist says that your data is my data is my data, right? So everybody wants their data to be on premise and the model to be on premise. So eventually everybody wants, and probably the enterprises don't need LLMs to solve the problem. All they need a SLM, which they can build in-house and host in-house. So as a industry, probably we should develop a skill set, a capability to develop small language models, deploy them, and if required, enhance them, fine-tune them. All these capabilities we should develop as an industry. That is what my thinking, and I have spoken to some of my friends and colleagues in the industry, and pretty much, at least, people who work in industry in the analytics domain, in the data science domain, the similar kind of thinking are coming up, shaping up, and sometimes people say the same thing in a slightly different way, but the similar ideas are coming up again and again. That model development in-house is going to be the next big thing that industry is going to face. So that is, on that thought, I am collaborating with you, with my senior colleague, Professor Ram Seshan, and he is going to lead this in this session. I'm going to do the running around. So with that, without any delay, Professor Ramsesh.
Okay. Thank you, Shoresh. Okay, let's start with a question, maybe one or two questions. So how many of you don't use ChatGPT or any of these? Yeah. You can't hear me? Can you? Okay, I'll use this as well. How about now? Okay, thank you. So how many of you don't use ChatGPT? Wow, okay. So all of you, right? Except Professor Madhavan. So what do you use that for? Are you replacing Google with that or doing something useful with ChatGPT or Gemini or what do you use that for? Okay, so are you replacing Google with that? So how many of you started using only ChatGPT for searching, getting information and all that? Good. So I think that's where the world is going. Okay, Google search is no longer alive. So even they are changing it. So those kinds of list of items and all we used to get right in terms of the links, they're going to go away soon. So what we are going to be getting is the list of summary of things that you are asking for. That would be listed as 1, 2, 3, 4 rather than the links and so on. Okay, by the way, coming back to the topic of the language models, the language models have grown pretty big, right? So the current Gemini 3 is about 1 trillion parameters. 1 trillion parameters in the 64-bit machine compute the number of bytes that you require to store and then use that, right? So it's becoming extremely hard to really do any research activity. For example, from the academy side, if I want to do something with the LLM, I think we can't really afford to have that kind of hardware capability to even do some inference part, because even for the inferencing, I require to load the entire model so that I'll be able to make some sense out of all my prompts and so on. So that's becoming very hard. And the data that we are talking about, like my data is my data, I don't want to give it. Even if I want to analyze my medical reports, I'm scared to really go to the Gemini and then do that, or ChatGPT and do that, because why should I give my data as a training data to someone else? So if I'm doing that even as a person, think about the organizations who have lots of information that they have gathered over the years. Why should they give it to some organization where they would use it for the general purpose language learning and then use it for their own benefits and so on, okay? So that's where the question comes in terms of, can I have my own LLM? So that's one of the questions that's been in the minds of many people, and then the answer to that is, okay, instead of an LLM, can I build one SLM? Okay, the small language model. Even to build a small general purpose language model, you require a good amount of hardware, and you require the general data set that all the language models use and so on, right? Now, thanks to many companies, they also started developing or giving away their small language models. Language model is nothing but a matrix, set of numbers. I think all of you are aware of that, right? They are nothing but numbers. So those numbers are all given away to all the folks so that we can make use of that. Now you can see many companies, right from Alibaba to Microsoft, developing small language models whose size is about 8 billion parameters to 0.5 billion parameters. Okay, so these are all the models that you can use in your own environment. So for example, if you are a little bit rich enough, you can buy a 64 gigabit Apple machine or Microsoft machine with NVIDIA card in it, and you can run your own small language model in that system. So what I tried to do for this session was I tried to build a small language model, not from the scratch data, but I want to borrow some small language model, which is already built, and then using that model, can I fine tune that so that it answers certain questions that I have? Okay, the data set, I'll talk about that a little later, but something, as a teacher, I would want to talk about this. We all have become API masters, right? So we don't know what is behind the scenes. And for you to build your own system, you need to understand something behind the scenes. You need to actually look under the hood to see what's going on. So I'm going to talk about the basics and fundamentals of that first, and then probably take you through the code. I won't be able to show you the training part of that because it's very slow, and it's going to take a lot of time for me to train a small language model, fine tune it, and then showcase that to you. The traditional masterclass is all about writing code, demoing, and so on, and I'm going to deviate from that part for this session. So I'm going to give the theory part first, and then I'll show you what kind of data I'm taking, and then what kind of data curation that I'm doing with that, and then how I'm going to be utilizing certain model so that I can fine-tune the data and finally have an inference engine that can answer certain queries that you have with respect to the data set that you have. Okay, so the important aspect of this small language model is you can build your own application. It'll be in your premise. It'll be within your control. Your data will not go out. You can pull the plug for the internet and it'll still work. Okay, how nice it would be, right? So that's something we want to have for all this. See, one of the tiny goals that we have, I think Saurish, I'm not sure whether he didn't mention about that, is to have this small language model installed in every school so that it answers queries related to mathematics, physics, and help them solve physics problems and things like that. Okay, so how nice it would be, right? So if you look at the kind of teachers that we have across the country, we can count the number of good teachers in physics, math, and so on. Okay, it's becoming rarer and rarer. So how nice would it be if we can build a small language model that is an expert in physics in terms of solving problems in kinematics or dynamics or heat, electricity, magnetism, and so on, and tell students how you can really go about solving it step by step and taking him through all the pains that we used to have to go to, right, when we were kids. So we want to have the same kind of experience for everybody, even in those who are in the rural side. So this is one of the goals. The second one is, for all the corporates who would like to keep the data in their premises, don't want to share the data with the LLM. For example, you want to build your application with the LLM, you need to share the data with them, right? That we don't want to keep. So we want to make sure that the LLM is being used, rather the language model, let me use the language model rather than LLM or SLM. Language model is being used to build your own application so that you can run your applications within your premises, for your own customers or your own people within the organization. Okay, so I'm going to talk about that in detail, but before that, let's so we need to know this first. I think I would like you to read this one very carefully. You shall know the word by the company it keeps. So this is the most important statement made in 1957, and we are here today because of this. Can you believe that? So what does it mean? So that means when you speak a sentence and the words are going to be having the correct meaning with respect to the words that are surrounding it, right? It's same as, you tell me about your friends, I'll tell you all your qualities of you, right? The same way. So that means we are going to be looking at the word not by just the meaning of the word that is provided by the dictionary, but in terms of the semantics. So we are going to be understanding each and every word in any sentence based on the semantics of the word. Okay, so the context is pretty important, and this is what John Rupert Foote said in 1957. That's when all these natural language processing tasks started in the computer side. Okay, this is the fundamental idea behind the distributional semantics that you're talking about. So every sentence that you see the ChatGPT generates has the semantics attached to it, right? It's all because of the context that it has understood. So now we are talking about 1 million words as the context to generate the next word. You know, if you go and then tell the small kid that you require 1 million words to fill in the next word, for example, when I say how are, you all can say that what would be the next word, right? So why do I need 1 million words to really find the next word? Sometimes, you know, it looks ridiculous to see the kind of context that we need to have to build a model which can give you the next word. Anyway, so this is the fundamental to the language model that we are talking about. And then the distributional hypothesis that we are looking at, words that occur in similar context tend to have the similar meanings. Okay, so for example, if I utter the word apple, what comes to your mind first? So how many of you say fruit? How many of you talk about technology when I say apple? Right, so if you look at the show of hands, you know, in many cases, in this case, fruit had more hands. So in the context when we are talking about, when I say, do you have the apple, then we are only talking about fruit. But if I say, in the context of technology, you'll say, okay, I have iPad, I have MacBook, I have all that, right? So the semantics varies in terms of the distribution of the data that you have. Okay, for example, in a corpus, if we have large amount of technology aspects talked about, and we had referred Apple, and the distributional semantics will always refer to Apple as the technology term and not as a fruit. Okay, so this is something which is very important, and I would like you to take a note of this. So this is something, you know, we always worry about. For example, when I mention the word bank, so how many of you think about the financial institution? Right, many of you. How many of you think about the river? So how many of you think about the airplanes maneuver, banking? Very few, right? So the semantics vary. So in terms of the airplane world, the banking varies. In terms of those, you know, who played cricket near the river bank, there the semantics varies. Those who, many of us, you know, who work in the bank or do some business with the bank means the financial institution which lends money, or I can deposit money and so on. So this is something which is very crucial for the language model. So this is something we need to understand. And the evaluation of the company started from way back. You know, we started with something called as a language model. It's not a new term. The language model is almost about 4 to 5 decades old. Okay, so we used to build language models using the kind of machine that we had, you know, 386 machines, maybe the VAX micros of the world and so on. We used to build those small language models using the probabilistic ideas, and we call them as n-gram models. N-grams is nothing but the context. For example, I can look at 5 words at a time, and then using those 5 words, what could be the next word that can occur? So I can use the statistics of my corpus to find out what could be the next word. So this is not very new. Okay, this is a very old concept. And then came all these models from the neural net world, where we can find the word embeddings. Again, word embeddings are all embedded in all the language models. We don't really talk about it, and it is one of the most important aspects that's there as part of the language model that we should be aware of. Then came all these a new one, the transformers, where we have the dynamic context-aware representation of the company that we mentioned in the first slide, right? So that one idea that started in 1957, now we have got the decades of progress. Now we have the large language model that only still looked at that you shall know the word by the company it keeps, okay? Again, the context, the company is now becoming the most important one, especially in the context of the transformer model that we have, wherein every time a word Apple is shown to the system, it looks at the context behind, maybe in about 1 million words, and then finds out in what context that Apple appeared. Then using that context, it will decide whether Apple should be related to a technology or it should be related to a fruit. Okay, so that's how the differences are made in the current technology. That's where we moved from here. There was no context here. We had only about 5 words that we can use to find out. And then came this again, about 10 to 15 words at a time. And here now we are talking about million words in context, but the company remains the same in terms of the distributed semantics. So the teacher, I think it's an important aspect. I need to tell you this. This is the most important equation right from the beginning of the language model we use. This doesn't change. Okay, so what it says is the probability of finding my next word depends on my context that I have, assuming that this is the entire sentence starting from word 1, word 2, word 3, and then up to word n. Okay, if I have been given the context of so many words, I can find my next word. So what is the probability of finding the ith word? So in all these transformer models or whatever language model that we have, this is what we are computing. And the number of words in terms of finding what could be the next word is limited, or sometimes it will be more. For example, when the system hallucinates, when the language model hallucinates, that means it has not really understood what could be the probable next word. His list of that probable next word is pretty long. So it picks up something at random and then starts hallucinating and so on. If it is very confident, the number of words that it might pick up would be in the range of 1 to 10. So that means when the numbers are less, then the confidence level of the system to generate the next word is pretty high. So this is something which we use in the old language models I spoke about. This is very inefficient because we have to really count only about 5 words at a time in order to find the context, and which was not really sufficient. It used to generate poor sentences. And then came another model. Again, if you want to understand what could be the next word, you need to remember what had been spoken earlier, right? So we need to have the memory part, which is very important. In the old scheme of n-gram models, there is nothing called as memory. Okay, so then if I don't have the memory, then I won't be able to remember what should be the next word. So I need to know what has been spoken. So for that, we brought something called as a recurrent neural net part. So it's nothing but a neural net model with a recurrent connection, which will help you remember this sequence. So the idea is, of this model is, theoretically, this can hold infinite number of words as its context. You remember, we need to know the set of sentences that's spoken in order to understand the next word that's coming out, right? For us to do that in the machine, we need to make the machine remember those words. So that remembrance is coming from the RNN, where we have a recurrent connection. That recurrent connection would enable the system to remember a lot of words. So one problem with this model is, it is a sequential model. With all the advent of powerful GPUs and multi-core machines, it can only do things in a sequential fashion. So to take care of the, rather to solve the problem, they moved on to something called as the transformer. So most of the language models now we talk about are based on this model. It came in 2017. And again, in this case, they talk about the attention. Attention is nothing but the extension of the context that we are talking about. So in the case of the transformer, each and every word that is spoken in a given sentence knows about every other word in this recursively. Okay, so there is no dearth of not knowing any of the words in terms of its context and so on. So this is one of the innovations that came in the neural net part. When this came in 2017, at the time all our machine capabilities also have enhanced. We have all the GPU powers and so on. Multi-core machines have come. For example, if you look at the laptop that I have, it's about 10 core machines with some 8 GPU cores and all that, and 16 GB memory in it, all that stuff, right? So now I should be able to do all the processing in parallel instead of in a sequential fashion. So in this model, we are able to do a lot of work with respect to doing things in parallel, at the same time remembering the sequence of words, and at the same time eliminate the recurrence part, whereas in the case of the old model, I think I forgot to mention that, it also forgets beyond a point. For example, if I'm talking for a long time, right? So you will not know what I spoke as my first sentence, right? It's very difficult, right? So for the model to remember my first sentence, so it needs to have an extended memory and it should not lose anything. So the way we perform the operations, maybe, let me take back. So what we do in all these models, neural net models, they are nothing more than matrix computations. They're nothing more than matrix computation. I'm sorry about that. They're nothing more than matrix computation, right? So they are just set of numbers that we are multiplying, and then we are just replacing those numbers over and over again. By the time it reaches certain set of sentences, it would have overwritten whatever it was whatever it learned earlier. So that's where the forgetfulness comes in the models, and that needs to be removed. So these models provide the capability to remember long sentences, sequences. For example, Gemini 3 claims that they can remember 1 million words, right? So in your chat box, you can actually have, very long chat. But I tried that for a few times, beyond certain number of, about 100,000 to 200,000 words, it freezes. It doesn't go beyond that. Maybe they claim within their own model they do it, but if you do it from your own system, try to chat with it, keep on adding more and more, ask more questions related to the same thing, and so on. Beyond a point, it slows down, and then you can see that it's starting to blink, without answering your question, or sometimes it takes a long time, or it freezes. So anyway, there are issues with these models too. It's not that they solve every problem on Earth. They all have problems. Okay, so next one. So the architecture I spoke about, just for the sake of knowing, I'm just giving the higher level architecture. It is stacked blocks of matrices, and then each block contains a self-attention mechanism. Self-attention is nothing but, if in a given sentence, if I say that if I take the first statement, stacked transformer blocks, so stacked will try to understand who is next to me, and it will try to understand who is blocked. In the same time, transformer will try to figure out who is stacked, who is a block, and so on. So they try to understand each other, and then that's what they call as the attention blocks. They do it for each and every sentence that they receive. So the way they process is, I'm sure you, I don't need to say this, all the training models happen based on a huge corpus. The corpus is containing close to about trillions of words, and they are fed in a sequence or blocks and blocks of text. And in each block, we have a set of sentences, and each sentence, we have set of words, and each word will try to understand what the other words in a given sentence. Okay, so that means you think about the entire sentence of 10 words, every word will know about itself as well as the other 9 words. So that means it repeats for the second word, third word, up to 10th words, okay? So that's what we talk about. And then there is something called as position encoding. When we speak a sentence, it's like a time series, right? So first word comes at time 1, second word comes at time 2, and so on. So I need to also make sure that it is coming in that sequence. My words are coming in that sequence when I reproduce. So it should know that these words, for example, each block, I should know that block is going to come after each. Okay, so for that, it should remember the sequence where it occurred. So that's where we have, and then there is something called as residual connection. So we'll not worry about that. This is to safeguard my update so that it retains the originality of the sentence. And then this is the equation that we use to find out the attention. Let me not get into that part. We have, these are the key components that we talk about: positional, residual, layer normalization, and causal masking. I think in the first session, we had seen this masking part as part of the large language model training. And then we have the positional equation as an equation. Let me not go into the details of that. I just want to make sure that, these are all things that we keep computing for every word, every sentence, and so on. Okay. Okay. So if anyone of you, require this, I know I can share this. I have my email ID given. You can write to me. I can share this one with you. Okay, so now, if I want to develop a large language model, we have to go through that process of training trillions and trillions of tokens, and we require close to about 8 to 9 months of training on a huge data center, right? So I was told that the data center for Grok, right, consumes the power which is equivalent to 1 month's power of Chennai cities. It's a per day consumption. So that how much they have in terms of their CPUs and GPUs. It's a huge city. It's a very big city in terms of the computers. So I don't know whether we should compare it with Chennai, or probably they should compare it with the New York city to find out how much power it really consumes and so on. So we don't want to get into those aspects, right? Even if I want to build my system, I need to have that kind of capability in order to build my language model. Let's not get into that. Let's try our poor small language model, which can do a lot of things really well, especially the specialized applications, okay? So I'm going to be talking about some of these ideas in the small language models, wherein the first part is the data curation. So I want to make sure that my data is clean. Okay, the data should not be junk, okay? So I want to have my data to be clean, so I just make sure that I clean the data in such a fashion that it is useful for my solution, okay? Then we're going to use the standard transformer, but we're going to use a very smaller one. And we're going to do the pre-training. When I want to build my SLM, I will do the pre-training on the curated data so that it is able to pick up the next token. As all the language models idea is only to spit out the next token, okay? And then we will do some kind of instruction tuning and alignment. Instruction tuning is about, okay, so I'll talk about that. Depends on the data to data, it's going to vary. Okay, it's not going to be constant. For example, I'm working on the Sanskrit corpus. The Sanskrit corpus contains a lot of books that are old books and palm-leaved scripts. They have a different kind of curation problems. And if I want to look at the budget data which I'm going to be using for this purpose, I need to clean the data differently. Okay, so it varies from corpus to corpus. So that's why, the person who is going to be doing this should know everything. It's not that he can only train. He should understand the data well. Unless if understand the data, you can't build your model. Okay, understanding data is extremely crucial. 70% of your problem will go away if you have the right data. Okay, so that's something we keep saying. And the instruction tuning is about you give a set of instruction, question answering. For example, in the case of budget, you may want to say that summarize the budget. When you summarize the budget, it should have these details. So you give some examples of that and then train the model so that the model generalizes that and then fine-tune that based on your instructions. Okay. So we're going to look at it from a very specific domain. I've looked at this aspect, I was just trying to figure out what sort of data that I should for this, choose for this kind of class, right? And then I found that our last year, the budget data was not that clean. This time, right from the 1947 till 2025, they have cleaned all the data, recreated all those. Earlier, it used to be just a scan data for 47 to 56 and so on. So now they have typed the whole thing. So now it becomes a lot easier. So that is one of the important aspect of curation. If probably they have understood that, maybe all these models are using it. So they thought the model should get the right data. They cleaned it up and finally gave a clean data set that's available, close to about 75 to 90 PDF files are available in that. I have that in this one. So you can look at the indiabudget.gov.in and you can get that. So next one is, all these PDF files, these are all good for presentation and so on, but LLMs don't require PDF, they require the normal text. PDF is not a textual document, but it's nothing but a set of pixels reconstructed to print things in a nice fashion. Okay, so we need to convert that. I use something called as PyMu PDF, and then I do some chunking, add metadata and so on. I'll probably show the examples from my code, how I'm doing that. And then we have something called as a LoRa fine-tuning. So this is one of the finest innovation that has occurred in the space of the language model. What we do here is we want to, the idea is to run all our applications in the laptop, right? So we don't want anything to be very big. So for example, most of the laptops now come with an 8 GB model, and I want to run my applications, which is going to use my SLM and should run on that 8 GB without sweating. So that is the idea. So what we're going to do is we're going to take a small language model that's already built, and I'm going to fine-tune that for my purpose. Okay, and then here for fine-tuning, we have something called as low-ranked adapters. The low-ranked adapters, what they do is, for example, if I talk about the small language model, they range from 0.5 billion parameters to 8 billion parameters. Okay, even they are pretty big, right? And again, if you look at the low-rank the small language models, they come in all shapes, from 64 bits to 32 bits to 16 bits to 8 bit to 4 bit. So why do they do that? Because if I take a 1.5 billion or an 8 billion parameter model, and if I have a 64 bit, it's going to be pretty large. Okay, so they reduce that to 32 bit. My resolution is going to be small. So think of this like a very high resolution JPEG image that you have, and you reduce the resolution. You still get the picture, right? It is not a pixel quality picture, but there'll be blobs and so on and so forth, but you get the picture. So they reduce the rank, but it retains the semantic qualities that is inbuilt in a given model. So we can take a model which is smaller. I've taken something from the Alibaba, which is called Quen, that they have very interesting models, and they really work well on Indian languages. Okay, I tried this in Sanskrit, and it seems to produce good Sanskrit sentences as well. I'm not sure what they did. So I tried Gemini. Gemini is supposed to be knowing all languages. They claim that the models have seen 175 languages. But I'm not able to get that kind of accuracy with respect to the Gemma. I think it's called Gemma, right? Gemma 2 billion parameters. But Quen 1.5 is pretty good for my Sanskrit sentence construction. So I thought, let me pick that up. And instead of 0.5 billion, I thought, okay, I have some luxury with my system. I have about 16 GB memory. Let me pick that up. And I picked up a 4-bit model, not a 16-bit or a 32-bit model. So the reason why I'm saying all these technical terms is, we need to know all this if you want to really build this system nice and good. So we need to get the right set, rather the models in order to try your application. Again, the one which works for me will not work for you. So you need to try, the Microsoft has got something called as Pi, a PHI, and then Google has Gemini, and then again, if you look at OpenAI, they have something for 1.5 billion, I guess. Some instruct models are available. So you have to try your own different models and then check how it works in your case. Once I have the LoRa for fine-tuning. LoRa is another interesting aspect. Those of you who are familiar with the statistics would know about PCA. Okay, so in the case of PCA, you can represent the original image or the original matrix with a very small rank. So in the same way, you can represent the data that you have in a small data set. For example, in this case, from 1.5 billion parameters, my model takes only about 0.35 billion parameters. So that kind of reduction that I have, the computation that I have to do with my machine, is shrunk to a small number when I do the fine tuning. So that is very crucial to know. So again, I have taken, instead of the PyTorch, the most popular machine learning library is PyTorch. Instead of using that, I'm using the MLX from Apple. The reason why I've taken that one is their library seems to have fused their neural models and everything extremely well in the MLX library. So I've taken that, but you can use PyTorch or any other library for your purpose. And then using the original model and then the fine-tuned, I get a fused model. That is your model that you want to use for your inference and so on. Okay, the model that I have fused is only about 200 MB. Right? So now that 200 MB can run in your mobile as well. Right? So that's how big it is. This is full of numbers, and it contains all the instruct sets that is available in the original model of Quen. And it also has the capabilities of the specialized data set that I have from the budget. So this is the power of the small model that I have. Yeah. So that's what I said, right? So it depends on your task. So for example, if we normally pick up something called as the instruct model. There are also general purpose model available. The instruct models are basically good for question answering. So if you are looking at solving some general problems, don't use the instruct. So use the general purpose one. So if you are looking at question answering, for example, you are having a customer facing application that needs to answer the questions of the customer, then go pick the instruct model. And you need to try and test. Sometimes, there is a bias. I am biased towards this because it worked in one case. So I have not tried Gemma with this. Maybe Gemma might have done a better job, but I'm not sure. But we need to try and then find out based on what quality of output it gives. I think you may have to choose. There is no real, because we don't know what kind of data set they used to train the model. So that's something we don't know, right? When they train their small language model, which I'm using, for example, Quen or Pi or Gemma or anything else, I don't know what is the data set they use to train the model and what kind of instruct set they use to train the model. Okay, so that's what I said, right? So depending on the kind of task that you have on your hand. Okay, so if it is a general purpose question answering, then you choose a general purpose model. If you want something on the instruct base, because they are trained to answer questions given the instructions and the answers, right? Yeah. Right. See that. Okay, so what is the kind of data that you have? That's the first question that comes, right? Yeah, so that means you can take that data set. For example, you have lots of frequently asked question that is already available, right? And you also have the all the manuals, everything loaded, and then all the answers are all available in the PDFs and so on. Yeah, you usually take the instruct model and then fine tune that. So that would be the right way to go forward. So the technology used is the low rank adapters that reduces the training drastically. And this is how it does. For example, don't worry about what it contains. The W is the matrix given by the original model. Okay, and then delta W is something that you have fine-tuned with your data set. And you're going to fuse those two elements so that this becomes your data set. Okay, so sorry, this becomes your language model. So again, this is same as the size of the original model that you have taken. For example, if I have taken 1.5 billion parameters of Quen model, your model also will be having the same size. Okay, so there is no change. So that means I'm retaining the characteristics of the original model and also bringing in the capabilities of my data set into that. Okay, so that is the idea of bringing in the LoRa here. So that is a math behind that. So what we have done here is we've taken the budget speech SLM. I have not taken all the data set because it takes a long time to even run this system. So I've downloaded all only for about 15 years from, yeah. Yeah. How does it deal with? Deal with the number? Right, so it reads the numbers as words. So it doesn't really distinguish, distinguish between the word and the number. It just comes, for example, if I say the defense budget spending is so many rupees, right? So if it just reads that as a sequence and then uses that in the context and then what could be my next word? Okay, so if there is a computation, yeah, they don't do well. So in terms of comparison, probably yes. So if you ask it to compute, what was the total budget allocation for defense from 1947 till today, so it'll give some numbers. I don't think you will believe that number. So they're not pretty good at. They are not computing machines. Yeah. Okay. Okay. So here I extract the text from the PDFs and then create the instruction following examples, and then inject some meta information. This is where you need to bring in your expertise into the data set. So don't think they can automatically solve all problems if you give them some data. They also need to be aware of what is the type of data that you are giving it to it, so that it can answer in a better fashion. So you need to inject. In my case, I just inserted year, minister, etc., just to test it out. And then I use something called as a JSON format. So here, my data set, I'll show the code that I have in terms of what the JSON type is. Every budget contains a lot of paragraphs, right? Budget speech contains a lot of paragraphs. Each paragraph, the assumption that I made, okay, so that may be a wrong assumption. The assumption that I made is every paragraph is independent. Okay, but that need not be true. Okay, there could be a continuation of the same discussion on the second paragraph. If I used only one paragraph to train, then I think my context is going to be lost. So that's why I said I need to be aware of my data extremely well in order to do all the fine tuning so that I get a better response from my SLM. Okay, so maybe I'll just show some, yes. Yeah, the factual, no, I couldn't hear you. Right. Okay, so I don't differentiate. I think it's left to the model to do that. Okay, so model is supposed to understand that. That's what I said, right? So when I provide the data to it in terms of the size, in terms of the paragraphs, so I need to be sure that a paragraph contains the contextual information within itself for that model to answer. So if the answer is coming from paragraph 1, 2, and 3, and if I had only used one paragraph for the training, meaning one at a time, then the model is not going to really do a great job. So that's what we call as the batches. For example, if you want to do your model to do a great job, you submit the entire PDF file as a batch, which is going to be extremely hard to run on the smaller machine. So for those who would like to build applications for your enterprise, don't depend on the smaller laptop of this type. Actually, buy a good hardware, maybe about 64 GB to 128 GB hardware, and you can build your models, which you can deploy it on a smaller system later. So in order for the machine to really contextualize everything within the data set, the batch size has to increase in terms of, for example, if it needs to compare the budget of 1993 and 2003, it should have had the batches loaded at once. But we don't do that. So it looks at each paragraph individually at this point in time. So it probably may not respond to your queries very well because of the limitations of my machine, not because of the model's limitation. Because the computation goes like this. In the 15 years of data, I counted how many paragraphs are there. There's about 1,583 paragraphs are there. And each paragraph is considered as a batch. So if I consider each batch and then I'm providing each batch to the system to train. So instead of providing one batch, if I had provided two batches mean my memory size will increase by 2 times. If I have 3 batches, then my memory size will increase because it needs to hold the whole paragraph in memory. So that's where the trouble is with the small machines and so on. So I limited this to 1 or 2 batches. That means it will remember only 2 batches, or rather 2 batches, I will use it for the fine-tuning purpose and so on. So again, when your developer is running this, you won't know when the right model is created. Okay, so there is no way of knowing it. So what we normally do is we just look at the training loss, and also we look at something called as a validation loss. For example, we differentiate two things. One, we send the training set to the system, and then once it gets trained, we have a validation data set, and then we use that validation data set whether it really responds to the data very well or not. The validation data set will have the answer also along with that. So if it answers well to that training set, that means, okay, let's go ahead. So the training loss and the validation loss, they have to come down during the iteration process. If they don't, for example, when the training loss comes down and then validation loss increases, that means we have done the overfitting. That means the system is not going to remember everything. It is not generalized. So I need to stop that training when the validation loss increases. Okay. So we need to look for a point where the validation loss is minimum as well as the training loss is at minimum. So we run it for about, so in my case, as I mentioned, right, about 1,593 or something that I have. So if I have to run it in 2 batches, I divide by 2, and then that many number of iteration will be considered as 1 epo. So that means 1 epo means it has seen the entire data set of 15 years. Okay, sometimes, 1 epo won't be enough. You run it for 2 times, 3 times, and so on. For it to complete 1 epo, it takes about 8 hours in this machine. Yeah. It might be doing already something, yes. Right. Okay, so that's where I showed you, right? What we do is we don't destroy the original model's data. The entire idea of the LoRa is don't destroy the data, but train the model on your fine-tuned version and then fuse it with the original one. So when you fuse it, you're going to be modifying some elements of the original data set, but we are not going to do it entirely because the number of parameters that you are updating is a lot less when compared to the original model size. So we have the control in terms of what kind of, what is the LoRa data size that I need to have. I can reduce that, increase it, and so on. For example, if I increase the size of my rank of the LoRa side, the original will start screaming, hey, you are erasing my data, you are erasing my information, knowledge, all that. So we try not to go beyond a point. Normally, 16 is considered to be extremely high. People don't usually try it. So 4 or 8, they normally stop.
So here what we have done is it's in a forward state.
No, I couldn't hear you.
We took a model and then we trained it with our own data.
Yeah.
And then
I didn't train that data. I just fused my
you
training
fused
with
the
that
data.
Mm.
Okay. Now I'm thinking of it as a customer agent where I'm using a small model for just supporting my household appliances. Okay. And I give it to all my customers and they start using that chat and then we get responses. So basically there is a feedback mechanism happening in the real world. And then I have to feed it back to into the model. So we took around 4-bit of data, right? So at what threshold should we look at increasing from 4 to 8 or 16?
Okay, so when you increase the size to 8, do you have a, so there, you tried this, right? What would be the right way to do it in terms of increasing the size from 4 to 8 and so on? Is there any? Yeah. Yeah. Okay, so here.
Yeah, so in our case, 4.8 didn't work. So then we moved to 32, 64, 128. 32 was overfitting. 64 was the best match. 124, again, it started degrading.
Because the original model's data is probably overwritten.
Yeah, maybe,
Yeah.
maybe. But my use case was very specific, which is information retrieval, which is named entity recognition and the NER relationships. So might be for that specific use case, 64 is the best choice, but could be for different use cases. Maybe different rank will be.
Okay, so it's going to vary from task to task, but the recommendation that I have seen in many cases, don't go beyond 16. So that's something that I've noticed, and in this case, I've used just 4. Okay, so 4 seems to work okay, but the inference, it takes longer time. It takes about for a word to come, it takes about a few milliseconds. So I can see the word, it keeps printing character by character and then starts giving me the entire sentence after 5 minutes after I prompted and so on. So that depends on, the capabilities, and maybe in my case of budget, it worked with 4. Maybe, that's what, these are all, there are no standard, procedures that you need to follow. You need to look at what is the accuracy that you are looking at. Are you getting the accuracy or not? Can I change this? These are all hyperparameters, we call it. You just keep fine-tuning them to find out what is your best match. Your best match may not work for me. My best match probably may not work for you as well. Yes. Yes.
So actually, similar hyperparameters are there for SLM and LLM also. It's just that few more hyperparameters. The way we did experiment with deep learning or other classical ML, we have to do similar experiment here also. Yeah.
Okay, so this is my code. This code is about, the reason why I didn't want to do the demo part is, anybody can be a masterclass presenter nowadays with ChatGPT. You go and then ask ChatGPT, give me a SLM model for my data set. It's going to give you code similar to that in about 5 to 10 seconds, right? So the code is not important. The process is important. The way, anybody can get this data, this code. And it's easy to try and then run it. See, some of the pieces of data I picked up, look at all this. I don't normally do this. Okay, so this is all coming from the model. Okay, so I tried the same thing. Okay, so I asked the LLM rather to generate the SLM code for me. Okay, so how nice it is, right? So I thought instead of going through the demo part, talking about the code, I thought I'll talk the internals of that, so it makes it a lot more easier for you to understand what goes on in the code as well, right? So let me go from the beginning. So here I have the data that is downloaded. There is the download code, and then I have the text extraction using the PDF, and then I'm creating the semantic chunks. This is what I talked about, the batches, right? So I'm assuming that my semantic chunk is one paragraph. Okay, so I'm creating my semantic chunk based on each paragraph in a given PDF, and they are all stored here. So they are all stored using some small meta information that I can ask. This is an instruct kind of an information. So what can you tell about the Indian budget? And then you are an assistant, and this is the content. Okay, so my data is curated in this fashion, instruction tuning fashion, so that it uses this during the training process, so that it can understand what kind of data that it sees in that particular paragraph. So for example, if you look at this, there are several paragraphs for the same year, you will see, in 2013 and so on. Okay, so each paragraph I'm considering, and this is what I feed to my model as my input. And then I also add additional meta information like, who is the finance minister. Sometimes you don't see, it's only say respected sir, and then they start talking about, there will be no mention of any of the finance minister. If you don't have this, and then ask the model who was the finance minister that presented the 2019 budget, it will say some Prashanti. Okay, so it doesn't really know. So it just makes up some word and then print. So you need to tell. These are all the secrets, or they don't tell you. So these are all something that you need to do as well when you create the model. It's not that you just push your data in and it's going to give you all the gold nuggets out of that. So you have to do some of this. That's why I kept saying you need to know your data very well. And as far as possible, if you're able to give more meta information, then your application is going to do a good job. So it is not going to do a better job without any of these. Okay, and then it also finds out if there are any duplicates that are available, I'll probably take it away. So I use some semantic ideas in terms of finding out what is the similar set of words. If it found in the paragraphs, if they are available, I just want to throw it away. But in this case, I have not found any. And then I process the PDFs to the JSON-L, and my main code comes here. This is where the MLX from the Apple has reduced my job. So if I had to write the code in probably PyTorch, it would be about another 100 lines more. In this case, it reduced my job a lot. I can just run the Python application of LoRa using this, which will train my system by adding additional documents and how many iterations that you want to have. So I given it as 792. It is not some magical number. I told you, right? So I have 1,500 plus paragraphs. So if I considered my batch size as 2, that means I'm going to take 2 batches at a time. So my one EPO is going to contain 792 iterations. So on. Okay, so and then it uses the data where the data is available, where my validation data is available, and then finally it needs the space to create my adapters. So when we use LoRa, what we create is the adapter. Okay, so we are not creating the LLM directly, we are creating the adapter. So the adapter is something that I'm going to be fusing with the original LLM that I have. Okay, so this, if you look at the adapter size, it's only about 200 MB plus in this case. Okay, it's pretty small. So that's where I have the luxury of having 2 batches in this case, and if I run this, it occupies close to about 4 gigabytes when it runs. Every iteration it runs, it says that I have consumed 4 gigabytes of the memory, apart from other operating system memories and so on. And if you look at the main memory consumption, it will be in the range of about 12 gigabytes. So the system, if you add 3 more batches, or rather add batches as 3, I think the machine will crash. So you need to be extremely careful about the system hardware in terms of specifying these parameters. And then every now and then I need the adapters output. For example, as I mentioned earlier, right, I wouldn't know when I will have the right set of adapters available. So I keep it running for 2 or 3 EPOs, and then I look at my loss and look at my validation loss. If they keep continuously going down, I'll continue to run the system. Otherwise, if I see a spike in my in my validation continuously, then I will stop. That means I am overfitting it, and no longer training is going to be very effective in my system. Okay, so this is the heart of the system, and we are running the code. It's a Python code, in fact. I can give all those. Pardon me? So this is integrated in within it. So when I use MLX, this Apple's one, they automatically use their GPUs as part of the training. So I don't need to specify anything. It's all integrated. So if I have to use PyTorch, then I need to specify use GPU or not GPU and all that. Whereas in this case, it's done. So since it also has a unified memory, I think it's doing a better job. I tried running the same thing with PyTorch. It was a bit slower. It is not as fast as at the Mac. So I save my adapters every 100 iterations to make sure that I don't lose the training. For example, if I need to shut down my machine and I want to restart the training, it can start from where it left using the existing adapters. Okay. This is the inference part that I have here. So I don't want to take too much time to show the inference part of that. So what I did, I just wrote a small application. I think the UI is forgotten. What we, the old timers probably would know. It's a TK toolkit, TK inter. I'm not sure how many of you remember this. So I used that to build my front end. The front end looks something like this. Okay, so I have a small front end, and I asked the query summarize the policies in 2019. It has done only about 700 or even less, and I don't expect this to be accurate. But in terms of generating the sentences and so on, they are good. I'm sorry, I keep forgetting that. So I found this to do something. I've not checked whether the data is correct or not. So I just asked the query, this might summarize the policies of 2019. And I'm assuming that it looked at the trained model and then provided something of this type. I think some are believable. I'm not sure how accurate they are because I've not trained yet beyond one epo on this. Okay, so again, for you to find the accuracy of that, you need to keep checking the evaluation part or the inference part now and then. Okay, so I rather suggest that you look at the inference part every epo and then check whether it is really giving you the right output or not. So make sure that you go through the entire data set so that it understands the whole set. Okay, so if you stop in between, then I think it probably may not remember everything very well. For example, if I stopped it in 1.5 epo, for example, about 1,200, then you wouldn't have seen the rest of the data set. So again, during the training, probably it wouldn't have captured the information related to the one that it left, and it may probably either hallucinate or give you wrong information and so on. So now I can train this. If I want to train this for 3 more days, I can do it without any internet or anything, and I can run all this in my laptop after the training is completed, after it starts giving the right output. Okay, so this is about the code that I have. Okay, so I think that's the end of my session. So if you want to build your small language model, so these are the experiments that you need to do. So you need to look at all standard models that are available. If you are looking for any question answering type of stuff, you always go for a instruct type of model. Try all small language models that are available, and then try all kinds of parameters that are available in terms of training, and then find out what fits you. Okay, so there is no sure cut way to find or fine tune the model without those hyperparameters, and I think they vary from model to model. Okay, so with that I close. If there is any other question that you have, I'll be happy to answer. Yeah. Okay, so these are all the models built for specific purpose. So they are not general purpose models. So the original model may have general idea, general knowledge about what you are asking. But this
actually, the question is not that.
uh,
So what I'm trying to ask is, if I'm building a support agent for my client, uh, the client is asking some question, and the model generated some output. Then the client is asking a follow-up question without all the things he mentioned before, right? So now it needs to have some context window, right? So as you said, the model size is reduced, and we are not using the as clear image, we are using that grainy image. Uh, how much it will affect my context window?
okay, so see, okay, just to answer a question, we have the general purpose model first taken, right? Like I've taken a Quen model, which you can use it for the general purpose chat. Okay, so it will answer all questions like what is 5 plus 3, it will respond. If you ask you what is the capital of Delhi, or rather capital of India, it will answer the question. So it has all the general knowledge available based on the data set it got trained. So what we have done is, we have taken a data set, in this case the budget, and we have fine-tuned the model based on the fine-tuning and based on which the original model was trained in terms of question answering. It is going to generalize the question that for example, you are asking questions of who was the finance minister in 1957.
Sorry to interrupt, but let me rephrase my question. I have built a chat assistant. Initially, my customer came and says that I have this particular error at this particular point.
Okay.
Okay. So now, based on the training data, I have feed the model. It gave some output, but now the customer doesn't have the clarity what it gave. Okay. So now the customer ask it, make it more clear. It is the only these three words. If the model is going to remember all the things which it gave the response and the question I asked previously, and it is going to generate a new response, or it has that much context window to process. That's what I'm asking.
Okay. Okay, so your question is, he is asking a question and it responded. Again, there is another question, probably, it didn't respond probably well, and he's
No,
rephrasing
I'm asking,
it type.
will it
Or,
respond well, and what is the context window?
See, the context window, that's what I said, right? So this is based on what is your data set. So it cannot answer anything out of the blue. So if, for example, the model that we have used, Quen, is a general purpose model. So it can answer general knowledge questions. Okay. So what we have done is, we have taken a data set. In your case, let's assume that all your errors related to some software. Okay. So that you have taken that as the data set, and you have fine-tuned the model along with the Quen's original model. So the model is going to answer with respect to all the information available in the data set that you have provided. Okay, so it is not going to answer anything out of the blue. Suppose if the question is not related to any of the fine-tuned one, It'll try to find the answer from the original model and then it'll try to answer, otherwise it's going to hallucinate. So everything depends on what data it is trained on.
Yeah, thank you.
Yeah. Yeah.
So let's say I have a problem domain where 98% of the data fits into or is available from a general public domain.
Okay.
Assume that I'm from a software based background. So let's say I'm working on C, Python, C++, that type of environment. But 2% of whatever stuff and data that I deal with is super niche, and it goes to the pattern of, that is my data and I cannot expose. Does SLM based system help me, or should I still go for some other type of, so let's say I have to develop a new program for a new problem that is.
So you want to answer even those 2% that is left out?
I don't want to expose that 2% outside, but 98% of my problem is like something, a general body of knowledge known to everybody.
Suppose if you are using Gemini for that case, and then let's say that it's all 98% of your problem. And if you don't want to leave your 2% out and you want to keep it within your organization, then either you can use Gemini, for example, you can license it, or I don't know the kind of license agreement they have, I don't know. Or you can look at models where you get the 90% answers. For example, Quen. Will Quen give me all the 98% answers? If it provides, then you can fine-tune Quen with your 2% of the data locally.
I mean, in SLM, for example, we are talking about 8 billion parameters. So the 98% of the problem is not generally addressed by that, right? I mean, for those...
We don't know that. It's difficult to know because they are also trained on the same data set that is available for the large language models. So only thing is they try to reduce they quantize it, or maybe reduce certain, for example, multilingual data, they will probably throw it away and probably keep only English and something like that. So the size of your language model developed for SLM probably would have covered all the stuff that you're talking about. So that's what I said. You need to really try with that, whether it really works or not. So it is very difficult to say. I think I mentioned about this. It's difficult to say what kind of data set they used for training. They won't reveal that to you.
Just a follow-up question on this. So let's say if I have to try a POC on this to address this particular problem domain, do you think it is better to start training in SLM, or maybe, as you said, get a proprietary license?
Try with the SLM first.
Okay.
Okay, so POC, it's a POC, right? So you don't want to spend so much money on to building that. So you can just use a laptop with about 16 GB or 32 GB and build your model using your data. And it's not going to cost more than the cost of the laptop or your time of about a week or so in fine-tuning and doing all that.
Just one more follow-up question on that. So this SLM model, for example, the model that you suggested, will it also be able to, let's say, answer questions similar to the way Gemini answers about, let us say, a prompt on Python or a C or a C# based thing?
Okay, so good question. I'm not sure. That's what I said. I don't know what kind of data set they used and what kind of instruction they used to train the model. For example, Quen probably wouldn't have seen all the code. Probably would have seen only the text part of it. So there is a specific Mistral, I'm not sure which one is it. So they are actually training the small language model just for the code. So you may want to try that if you want to have a specialized version for your code.
Okay, thanks.
Yeah. Right. 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 Okay. So RAG based, you just want to be within the boundary, right? So you want to have the guardrail, and then you want the model to answer only the questions within the, yeah, right. So you probably would go, extend this to the RAG model, and then probably do that, since it's going to be a small extension to what we have here. So I can also build a RAG model based on the Indian budget, and then when I ask any question other than the budget, it will say I don't know anything about that. So it will only try to answer within that. So you can build the RAG model and then put the guardrail around that to answer. An extension of this, yes. You can use the same fund model to build your RAG as well. So one of the RAG models that I built was for the Chanda Mama in Sanskrit. So we have about 175 versions of Chanda Mama published from 1987 till I think the last one they published. So we built the RAG model, and it kind of answering questions within the small data set. So we are not pretty happy with that, because most of the models are not really trained on the Sanskrit very well, but the kind of response it gives is encouraging, so that now we can move further in that direction. So maybe, in the case of English, in all the compliances are going to be in English, I think these models would do definitely better. Maybe I would suggest you to look at Gemma or Pi in that case. I'm not sure about Quen, whether it had seen every kind of language that is used in English in terms of usage part. Okay, so that's a very difficult question to answer. Which model to really try? We don't know yet. So you need to do the trial and error. When somebody suggested use Pi to do this, Pi did not answer some of my questions well, but Quen did a better job. So I stayed with Quen. So even though it's from China, that's fine. No, that's what I said. You use the SLM to build your RAG. So the same thing. So when you are interested only in answering questions with respect to your domain, nothing else, go with RAG. Okay. So RAG based, basically what probably would have done is you would have done some semantic search and things like that. Okay, so if you want to really have an English-based answering questions well and things like that, I would rather go for an SLM and then do that. It will be very fluent in terms of responding. Whereas in the case of no SLM, but I have RAG means, I'm not sure how really it responds with respect to question. Maybe it will pick up paragraph and then show it to you. It probably may not be a conversational type of English that you will find.
So, here.
Yeah.
Sorry?
Right.
Yeah, sure.
So, okay, to improve the accuracy, what can be done? One thing you want to do is play with your hyperparameters. Okay, so that's something I tried, changed, and things like that. And also, you need to watch your training loss versus the validation loss. How is it going? So it's a very painful process. Every time you change the hyperparameter, you start afresh. You'd go through the entire iteration of 4 hours of training and then see how it goes, and then you stop and then do the inference part and then see how the accuracy is, because that's how we can figure out, not just by the laws and so on, right? And then have this done for 2 or 3 such combinations of hyperparameters, and then find out where it is doing better. And so unfortunately, I have no mechanism to really pinpoint, okay, do these, you get the better accuracy. I think at this point in time, there is no answer for that. Yeah, technology moves in a faster way, so I can run this a lot faster, but I still have to do this. Maybe, some a smart fellow would probably find a better way to do this. Maybe a transformer model may evolve better and may probably do better things.
So, one question just.
Yeah.
Yeah, sure. Just one last question. So, I mean, I would like to extend from, the statement that you said that the SLM will take the numbers as a word. They take numbers as a word. So, do they do the same for
No, no,
codes as well?
okay. So I think probably we have to have a longer conversation on this part. The numbers are the words are represented as vectors. Okay, so if you look at the transformer, the standard transformer model represents the word as a 512 element vector. Okay, 512 element of floating point numbers. That's how every word is written. For example, there are several billion words, and we have several billion such vectors available. And these vectors are semantically having information about every word in the corpus. For example, I have mentioned if I consider 1 billion words in my corpus as my vocabulary, and every word in the vocabulary will have information about every other word in the vocabulary. Okay, so that's the example I gave you in the beginning, right? So if I choose Apple, and then if the entire corpus is about technology, then Apple would always represent the word technology. It will have words iPhone, iPad, everything closer to Apple. Okay, so if I had had a corpus that contained lot of information related to fruits, then fruit word, rather the Apple word, will have information related to, in terms of similarity I'm talking about, the raspberry will be closer to Apple. Okay, and then grapes will be closer to Apple and so on. So the context varies in which they appeared in the entire corpus. So that's where we have the transformer model, wherein it looks at the context of about 1 million words and then tries to find out whether it belongs to the technology side or to the fruit side, and then associate the word vector along with that.
Sure, sir. I have a question, but I think we are out of the time. So
Maybe after that you can.
yeah, sure, sir. We can connect off.
I think with this we close today's session, and again tomorrow we will start at 9:30.